In my last video, I talked about how the double slit experiment was mind-blowing. How the particle passed through the slit depended crucially on whether someone was detecting the particle or not. In this video, I'm going to show you how scientists can not only undo that effect, but how it's related to time. Let's take a look, shall we? So we're about to tackle a very tricky concept in physics, which involves the nature of space and time and whether the future can affect the past. But this is so tricky, I think it would be best if you viewed my earlier double slit experiment video. A link to the video is given in this video's description. Go ahead and watch it. I'll wait. We saw in the previous video that a single photon traveling through both slits leaves an interference pattern, which means the photon is a wave. If we looked at which slit the photon goes through, we see a pattern that is consistent with the photon being a particle. We call the second experiment a which way study. This result is pretty freaky. Back in the 1930s, physicists like Niels Bohr speculated that human consciousness changed the result. We no longer believe that. Any detection of the slit the photon goes through gives the same result, including detection by electronic circuits. Of course, the earlier speculation led to a lot of quantum woo, ranging from the books The Dancing Wu-Li Masters and The Tao of Physics, to more recent films like John Hagelin's portion of the movie The Secret, to What the Bleep Do We Know, to much of what Deepak Chopra writes. None of any of these things are in agreement with modern science. Sorry if they resonated with you, but you should discard all of them. But let's make some changes to the single photon hitting two slits experiment. They're going to blow your mind, I promise. Let's add a crystal to the experiment, which turns the incoming photon into two photons, each with half the energy of the first one. These two photons are what we call entangled, which means that if you measure one, you know everything about the other one. The fact that one is yellow and one is red isn't real. They're actually the same color, but I use the two colors to clarify what I'm talking about. We then add two detectors called A and B, which measure not the photon hitting the screen, but rather which slit the photon goes through by measuring the cousin photon, which never hits the screen. If A and B are turned off, you see a wave pattern. That kind of makes sense, but if A and B are on, and you look to see which slit the photon went through, you get a particle pattern. Okay, here's the first mind blower. Suppose you make the cables going to A and B very long, so the photon hits the screen before you can measure its cousin in A and B. If you do this, the result is unchanged. So what does that mean? It means that if you turn A and B on, detecting the cousin photon affects what the photon hitting the screen does in the past. This experiment seems to completely screw up causality. The particle or wave pattern is created by whether a detector in the future sees which slit the photon goes through. But there's yet another step in weirdness. What if you can erase your knowledge of which slit the photon goes through? What happens then, and how do you do it? You do it by adding 3 half-silvered mirrors. A half-silvered mirror will reflect half of the photons and half will pass through. You put 2 of them, one in front of the detector A and one in front of the detector B. This means that the beams of cousin photons can go into the detectors or get passed along to additional instrumentation. You also add 2 new detectors, C and D. These are farther away from the screen than the A and B guys. You place mirrors in front of the beams of cousin photons, leading into a single half-silvered mirror. That means that the photons from A can either be reflected into detector C or pass through the mirror to detector D. Conversely, the cousin photons from B can either be reflected into D or pass through the mirror to detector C. You can see it in the red and yellow paths. C and D can see yellow or red. The bottom line is whether you see a cousin photon from detector C or D. You don't know which slit the photon went through. The addition of C and D completely erases the knowledge that A and B give you. So what happens if you turn off detectors A and B and look at only C and D. Since the detectors don't tell you which slit the photon went through, it once again acts like a wave. But C and D are a little offset, so you see the interference pattern only when you look at C and D separately. Furthermore, if the cables to C and D are long enough, the photon's hitting the screen long before the cousin particles hit C and or D. So what I'm saying is the following. If you use A and B in the original experiment, you get a particle pattern. However, if you use C and D in this new version, you get a wave pattern. And detection in A, B, C, and D all happen after the interference or particle pattern is created. This bizarreness implies that in the quantum world, both location and time don't act like they do in our familiar world. Quantum mechanics can be considered non-local because of the cousin photons, and non-temporal because the detection somehow changes the past. Now, the most important thing to state is that these are experimental results. You can discuss what they mean, but you can't deny that this is how the quantum world works. Because without any chance of being wrong, this is how the quantum world works. So how can we explain the delayed choice and quantum eraser experiment? The simple and sadly unsatisfying answer is we don't know. However, I have given a ton of links to other descriptions of the delayed quantum eraser experiment that you can find in the description. Okay, so what's the answer? Like I said, we don't know. Could it be that the universe at the quantum level doesn't understand time in the way that we do? Is the universe super deterministic, which means that everything we do, past and future, is predetermined? Or getting even sillier, maybe the delayed quantum eraser experiment is just a bug fix in our simulated universe, which is kind of like the Matrix. Or it could be none of the above. Indeed, it almost certainly is none of the above. The real answer is almost certainly going to make all of our heads explode. Okay, so that was cool. I'm sorry that there's no answer, but there isn't, even for people like me. And for those inquiring about the weight loss, you wouldn't believe how much a mustache weighs. It was time for a change. The last time I was mustacheless was not quite 40 years ago. I haven't decided if the mustache will come back or not. Feel free to comment if you have a strong opinion. In any event, if you enjoyed the video, please like, subscribe, and share. And tell all of your friends who enjoy having their mind blown. These are also probably my kind of people who know one of the key truths of science, which is, of course, that physics is everything.